Welcome back! In the previous video, we finalized the Mark-8 minicomputer and ran some tests to verify its basic operation. In this video, we will conduct additional testing to ensure that all components of the minicomputer are operational. Let's return to the original Mark-8 construction manual to finish the testing procedures. We left off by running a simple register increment program. The next procedure will test the operation of the output register. If we look at the Figure 5 schematic, we can see that data from an output port comes into an SR latch and latches it in place. It's only operating on D0 and D1 pins of the port, and the rest are ignored. The output from the SR latch is then inverted and allows it to drive a lamp through a transistor. If D1 is high, then Q will be latched to high, and the lamp will go out. If D0 is high, then Q will be latched to low, and the lamp will come on. Using this simple circuit, we can toggle a lamp on and off based on whether the output sends a 01 or a 10. Here I have built the circuit as described in the manual and hooked it up to an output port of the Mark-8 minicomputer. I'm using a 74LS279 for the SR latch and a 74LS00 for a NAND gate. I also have a blue LED with a current limiting resistor, which will be toggled as we run our program. Notice that I only have pin 0 and 1 of output port 2 connected to this circuit. Let's take a look at the program that will toggle the LED. It will first load an immediate value of 1 into register A and then output it to port 2, the first 2 bits for 1 or 01. Next, it will load an immediate value of 2 into register A and then output it to port 2. The first 2 bits for 2 are 10. Finally, it will perform an unconditional jump to address 0 and restart the program. We will single step through this program to demonstrate how it works, since running it at full speed will not allow us to observe the toggling of the LED. Let's go ahead and enter the program into the computer. Set the computer to step mode. Set the switch register to 005 and switch out of jam. Now toggle interrupt and let's single step through the program to observe the LED. The LED is toggling as expected. With this simple test, we have verified that the output port is operational. With this setup, we are able to toggle up to 4 devices on a single output port. Fortunately, there's a way to drive many more devices by utilizing a decoder, as described in the manual. This circuit receives data from an output port and runs it through a 7442 decimal decoder. If we look at the datasheet for this IC, we can see that it's possible to toggle up to 10 devices using just 4 bits. If we use 2 of these ICs and a few NOR gates, it's possible to drive up to 128 devices in 2 states. Here I have the circuit built on a breadboard, as described in the manual. I'm using 2 7442s, a 7402 IC for the NOR gates, and a 7400 IC for a NAND gate. Let's enter the program outline in the manual and try to run it. As we single step through it, we can see that the LED is toggling as before, but this time we're able to control many more outputs via a single output port. Alright, let's move on to the experiments, the first of which will test the input ports. The Mark-8 has 3 input ports, but one of those ports is used by the CPU, so it really has 2 input ports that we can use. In the first experiment, we have some jumper wires connected to input port 1, and right now they're all connected to ground. The program that will run will read the data from input port 1 and move it to register A. It will then output register A with the data it just received to output port 0. Output port 0 is actually on the bottom row of the LED register display board, so we will be able to see the data directly on the LED register display. The last instruction is a halt. Let's enter the program and run it. As we can see, when the program is executed, the output port 0 register display is set to all zeros, since that is what is coming in from the input port. What if we set the input port value to something else? Let's say A1. Toggle interrupt on the computer. Notice that A1 is now displayed on the output register. We can perform a few more tests to ensure all bits are coming through correctly. Let's change the program slightly. Instead of halting, let's make it jump back to address 0. Now, if we run the program, the output register will display the data coming in from the input port in real time as we make changes. This simple experiment has verified that our input port is operational. Let's do something a little more interesting with the input ports. What if we write the input data into memory on each interrupt? This can be achieved with the following program. First, it loads register H with 0 and register L with 100 octal. This HL register pair will be used as an address pointer to point where the input data will be stored in RAM. The starting position is at RAM address 100 octal. Next, it inputs data from port 1 and moves it to register A. It then outputs register A to port 0, which, if you remember, is the LED register display port. Next, it moves the contents of register A into the memory location defined by registers H and L. H are the higher order bits and L the lower order bits. It then increments the value in register L by 1. So in the first iteration, the value in register L will change from 100 to 101. And finally, it halts the program. The last instruction is a jump instruction, which will jump to address 4, the data input instruction, and run the program again starting at address 4. To execute this instruction, interrupt the computer with the switch register set to 300 after it has been halted. This will continue the program from where I left off. Notice that I'm inserting a no-op instruction between the load data instruction and the increment instruction. There seems to be a timing issue causing the program to fail without a no-op. This no-op, or a few of them, inserts a delay into the computer by making it run a few cycles between operations. A no-op instruction is a no operation, so it doesn't really do anything. Let's use the same setup as in the previous experiment. We will define the value of the input register by setting each bit to either positive 5 volts or ground, a 1 or a 0, with a jumper wire. Let's go ahead and enter the program into the computer, remembering to insert a few no-op instructions after address 6. With the input data set to all zeros, let's run the program from the start. We can see on the output register that the value is 0. The 0 value should have been copied to memory address 100, and we'll verify this later. Let's change the input to something else and then change the switch register to 300. After that, toggle interrupt. This continues the program from the last halt and makes it jump back to address 4 to read additional data. The output register now shows a 1, the value that we inputted. Let's insert a few more values and then verify the data in memory. Stop the program by putting it in jam mode and select address 100 to examine the contents of that memory address. It's showing a 0, which is what we had inputted initially. Let's examine the next few locations to verify their values. It seems to be showing the correct values, the values that we had inputted initially. This experiment has verified that the input ports work and that we are able to write the data received in the input ports to RAM. You may not be wondering where this is heading. What if we hook up an ASCII keyboard to this computer and capture entered keys into RAM? We can then act on these values by writing a program to read the captured keys. Stay tuned to see the result of that later in the video. Let's move on to experiment number 2, which will light up LEDs based on which outputs are high. The circuit is pretty straightforward. It uses a hex inverter to invert the signal, which then toggles the LED for each bit. This will only handle the first 4 bits, although additional bits can be managed with a few more inverters. Since I don't have hex inverters, I will use a 7400 quad NAND gate IC to act as an inverter. It comes with 4 gates. Here's what it looks like on a breadboard. The program, which we can reference in the manual, is only 3 lines of code. It inputs data from port 1 and moves it to register A. Then outputs register A to output port 3. Finally, it halts the program. Let's enter it and try running it. With the input set to all zeros, the LED lights are all off. Let's change the input to 1 and rerun the program. As we can observe, the LEDs display a binary 1. We can try this with a few more values. Let's now change the program to loop back to address 0 instead of halting. This will make it run continuously and change the output in real time. I will add a few no-op instructions between the out instruction and the jump instruction for timing. With the program running, let's change the input values. As we can observe, the output LEDs change to reflect the input selections in real time. Further on in this experiment, there's a block of code that checks the value of the input and halts the program if the value received is specific. For example, if the value received is binary 1110, the program halts. If the value is something else, the program jumps back to address 0. Let's enter this program into the computer. Remember to insert a no-op between the input instruction and the compare instruction for timing. Set the input to all zeros and run the program. It appears that the program is in a loop, which is correct. Let's change the value to something else, for example, a 1. We can continue changing the values incrementally until we reach 14 or binary 1110. Notice that when we select 1110, the program halts and no longer runs. With this simple program, we can control a valve when a tank reaches full capacity. We can also use it for other purposes, such as listening to a strobe to indicate that there is data on the input port. The remaining experiments in the manual are interesting and should be attempted to get a better understanding of how the computer operates, but we are going to skip them in this video. Now let's try connecting a keyboard to the Mark-8 and output the encoded ASCII received from the keyboard to the output register. The connections are very simple. Input port 0 will read the 7 data lines coming from the keyboard with the 8-bit grounded, and input port 1 will read the keyboard strobe line, which goes high whenever there is valid data on the data lines. The program that we will run is also simple and similar to other programs that we have already executed. The first line reads the input from input port 1, the strobe input, and moves it to register A. It then compares the value to see if the value received is a binary 1. The next line jumps back to address 0 if the value is not binary 1, meaning the strobe is not set. If the strobe is set, the jump instruction is ignored and the computer moves on to the next instruction to read data from input port 0. We can add a no-op for timing. And then we output the data received to output port 0, which is the LED register. Finally, we jump back to address 0 to listen for a strobe again. The octal format is on the right side and we can use that to enter the program into the computer. The keyboard I'll be using is a Cherry ASCII keyboard from an old terminal. It's missing some keys, but I have verified that it works. I received this keyboard from Steve Binder, a viewer of this channel. Thank you for your contribution. The connections on the keyboard include a positive 5 volt, ground, keyboard strobe, and 7 data lines. The positive 5 volts and ground are connected to the backplane power. The 7 data lines connect directly to the input lines of input port 0. The 8-bit is jumpered to ground since it's not used. The K strobe is connected to bit 0 of input port 1. The remaining bits are grounded. This is important. Let's enter the program into the computer and execute it. Watch the output register as we type on the keyboard. Notice that the output register displays a value, in this case 110 octal. If we look at the ASCII table and reference the letter H that we just pressed, we can see that the ASCII bits for H are binary 100, 1000, which is 110 in octal. So it looks like it's reading and outputting the correct ASCII for the key that was pressed. Let's press another key. Notice that it's showing all ones on the output register. This is because when the key is released, the strobe is read as being high, but by the time the program reads the data from the data input line, the data is no longer there. The way to fix this is by using a monostable multivibrator. The document mentions this by suggesting the use of a 74123, which accepts a strobe input and then the output connects to input port 1. This will do a quick toggle whenever the strobe line goes high and then go back down to low to prevent the program from reading a high when it already read the key press. Unfortunately, I don't have an extra 74123 on hand at the moment. We can still type on the keyboard and get most of the keys to work even without the 74123. As a challenge, see if you can write a program that will store the ASCII format of the key press in RAM as the keys are pressed, incrementing the RAM location with each key press. While this method of capturing keystrokes works, it's not the most efficient approach since the computer is running in a loop unnecessarily. A better approach is to utilize interrupts. To do this, we can connect the strobe to the external interrupt line, which, if you recall, is labeled as letter P on Brian Blackburn's wire connection diagram. We will also need to specify the restart instruction on each key press. The 8008 CPU supports up to 8 restart instructions, each starting the program at a specific memory address. Notice the first restart instruction, the 005. We have been using this instruction to start all of our programs so far. This restart instruction, when the interrupt is toggled, starts the program at address 0. If we write a short program to capture keystrokes from a keyboard and place it at memory address, let's say 020 octal, we can enter 025 in the interrupt instruction port, or the switch register, and toggle the interrupt with the keyboard strobe line. This will execute the program at memory address 020 octal. The Mark-8 document provides an example circuit on how such a setup can be implemented for a keyboard input, and any other external device that might be connected to the Mark-8. We will implement such a solution in a later video, but if you would like to give it a try, I think it would be a good challenge to attempt. That is all for today. Thank you for watching this video. Don't forget to like and subscribe, and I'll see you in the next one.